Hey guys, so this is section 7.3, the compression factor Z. So let's start out with the definition. Z, the compression factor, is defined as the molar volume of a gas divided by the molar volume of an ideal gas. Usually we write it this way because for an ideal gas, PV equals nRT, where n is 1 for the molar volume. And so that means V equals RT over P. Substitute it in here, and we get this expression right there. So if the gas is an ideal gas, then Z is equal to 1. So at the same values for temperature and molar volume, we can say that if the compression factor is greater than 1, then the real gas exerts a greater pressure than an ideal gas would. If the compression factor is less than 1, then the real gas exerts a lower pressure than an ideal gas. So this graph shows the compression factor versus pressure calculated using the Redlich-Kwong equation at 400 Kelvin and the van der Waals equation at 400 Kelvin right here. And the Redlich-Kwong equation at 200 Kelvin, the van der Waals equation at 200 Kelvin. The dots are real, these are the real values. So we can see that the compression factor depends upon temperature because it's a different form at 400 Kelvin for both of these equations than it is at 200 Kelvin. Also, the compression factor goes to 1 as the pressure goes to 0 right there, which makes sense because as the pressure goes to 0, and in the limit, as the pressure goes to 0, there aren't going to be any interactions between the particles, and the particles will take up, very little volume, which is, an ideal gas. It ends up with the Redlich-Kwong equation. We get really good prediction of behavior in this region at 200 Kelvin, but once you go past about 175 bar at 200 Kelvin, you get nonsense from the Redlich-Kwong equation, so it doesn't work past that, basically. So for van der Waals gas, what we're going to do is we're going to look at how the compression factor varies with the pressure and what it tells us. So we're going to start out with a definition of the compression factor over here, and we're going to substitute the pressure of van der Waals gas, RT over molar volume minus B minus A over molar volume squared, for the pressure. So that's what this is right here. That is just the pressure of a van der Waals gas. And do some substitution and rearrangement. Basically, write these terms separately over RT, and we get, the RTs cancel here, distribute the molar volume inside, and we get this expression right here. So that's the compression factor for a van der Waals gas. This is the pressure of a van der Waals gas. Okay, the reason we want those is because we're going to look at the variation of the compression factor as pressure changes at constant temperature, partial Z, partial P, constant T. It ends up, it's convenient to write this in an equivalent form, where basically we divide by the partial of the molar volume on both top and bottom of this expression. Because partial Z with respect to molar volume, we can do that here. Partial P with respect to molar volume, we can do that here. So, partial of the compression factor with respect to molar volume, it's this top, the blue part up here. This is just, basically the chain rule, and substitution too. Likewise, partial P, which is this term right here, with respect to molar volume, gives us this term down here. That's this right here, which is equivalent to partial Z, partial P, constant T. So this is what we got up here. Now just doing a little bit of algebra. Multiplying by molar volume minus B over molar volume minus B here, which is just 1, we get this expression. And that's nice because now we have two terms with the same denominator. The molar volume here and here cancels. We get minus B over this. And this is the same. Denominator is the same too. 'All right. So this is what we have at this point. Partial z, partial p, constant t is equal to this expression. Now what we're going to do is look at what happens in the limit as the pressure goes to 0, which an equivalent way of saying that is the limit as the volume goes to infinity, right? Because as the pressure goes to 0, the volume goes to infinity. Same thing. So we're going to take the limit of this expression as the molar volume goes to infinity. And so what we're going to do down here is some more algebra first. I'm going to separate the terms. So this term over this whole denominator plus this term over this whole denominator. That's what this is right here. The molar volume minus b squared cancels here. We get b over RT minus, then the molar volume minus b squared appears here and there. And likewise over here with the a term. Now we take the limit as the molar volume goes to 0. Let's look at this. First of all, as the molar volume goes to infinity, as the molar volume goes to infinity, it's so much bigger than b that molar volume minus b becomes just the molar volume. And so this term and this term cancel each other out, and this is just 1. That's why we get the RT squared here. This term here, as the molar volume goes to infinity, goes to 0, so it goes away. This term here, as the molar volume goes to infinity, the denominator goes to infinity faster than the top term does, and so this goes to 0 also. And so we end up with something really simple. The limit as the molar volume goes to infinity of partial z, partial p, constant t is equal to this expression right here. And we're going to rearrange this just a little bit. And that's a pretty simple expression. Remember, the a is the and the b are both van der Waals coefficients. Then they depend upon the gas. So this is what we got. We see that this is equal to 0, which is the slope of the compression factor versus pressure curve as p goes to 0. This is equal to 0 when b is equal to a over RT. Or, rearranging that for the temperature is equal to a over b times r. Remember, a and b are van der Waals coefficients. R is a gas constant. That temperature, that's a very specific temperature. That's an important temperature. That's called the boil temperature, TB, and it's equal to this really simple expression right here. So let's look at the boil temperature, what it tells us. So, partial P, partial V, constant T, the limit as the pressure goes to 0, it's always positive at high temperature. And we can look at this expression here, because when at high temperature, this term here, this whole term here becomes really small, and it just goes to B, and B is always a positive number as temperature goes towards infinity. So that means that the partial of the pressure with respect to the molar volume at constant temperature at high temperatures is always positive. That's going to tell us something. When T is equal to the boil temperature, T equals TB, that's the only time when a real gas will exhibit ideal behavior as the pressure goes to 0. When the temperature is a lot greater than the boil temperature, then the repulsive part of the potential, the attractive potential, dominates. And that's really all the molecule feels. That's the B term right here, because when, like we just said, when T gets big, this goes to 0, and we just get B here. When temperature is a lot less than the boil temperature, then the molecules only feel the attractive part of the potential. That's the A term right here, because when T gets small, this term gets big. And also, another important thing to get out of this is that at high pressure, Z is always greater than 1 for all gases, which means that the repulsive part of the potential dominates, no matter what the temperature. That's at high pressure. And that makes sense, because you think about what happens when it's high pressure, though. These molecules or particles are being pushed together, and so that repulsive part is gonna become really important. All right, so let's look at this graph here. I kind of have a lot of stuff on here, but this is at 400 Kelvin. This is 3 different gases, all at the same temperature, 400 Kelvin: hydrogen, oxygen, and ethene. And this is The lines are from the van der Waals equation, the dots are the real behavior. So we see that the partial of z with respect to p at constant t and the limit as pressure goes to 0, so right up here. So the slope of this line for hydrogen is positive, for oxygen it's about 0, and for ethene it's negative. For hydrogen, okay, because the slope of this line is positive, that tells us that the repulsive part of the attractive potential, or the repulsive part of the potential dominates, and so that means that we're a lot bigger than the boil temperature. The temperature is higher than the boil temperature at 400 Kelvin for hydrogen. For oxygen, the temperature is, because the slope is about 0, that tells us that we're really close to the boil temperature. And for ethene down here, because the slope is negative, that tells us that the temperature is a lot less than the boil temperature and the attractive part of the potential dominates. So this over here on the right hand side is important. This is the takeaway. If the partial z, partial p, constant t is less than 0, and the limit as the pressure goes to 0, then the temperature is less than the boil temperature and the attractive part of the potential dominates. If the partial z, partial p, constant t, limit as p goes to 0 is greater than 0, positive, then the temperature is greater than the boil temperature and the repulsive part of the potential dominates. That's the compression factor.